So for question 3a, this raises an interesting point because I don't have a closed interval, so I can't plug in infinity, and yet I'm still curious as to know what's going on at the endpoints. So I might start with that. I'm going to do this three ways. Number one, I'm going to look at what's going on as x approaches infinity for this function, and what's going on as x approaches negative infinity for the function. Right, since I can't plug in the endpoints, I'll at least see what's going on. So as x approaches infinity, this function goes to infinity. And as x approaches negative infinity, right, that's also going to infinity. So I can even guess what this is looking like. But I know one thing for sure, there's going to be no absolute max, because you can't get higher than infinity. So then let's look at our critical values. We know what's going on here. We're going to have 2x minus 3. We'll set that equal to 0 to find the critical value, so that gives us x is 1.5. And I'm going to plug 1.5 into this function, and it's going to give me whatever it's going to give me. I don't feel like doing this, but let's do this. So 1.5 squared minus 3 times 1.5, and then minus 1. It's going to give me negative 3.25. And as far as our competition is concerned, that is less than infinity. And the only thing that it has as its competition is infinity, so this must be the absolute min, is negative 3.25. And that happens at x is 1.5. Okay, here's another method we could use though. Another method we could use is, even if we disregard the endpoints, what I know is that if we were going to do the first derivative test, I can tell that if I plug in, I'm going to label this f prime, if I plug in any number to the left of 1.5, that's going to give me a negative first derivative over that whole interval. Anything greater than 1.5 is going to give me a positive first derivative over that whole interval. So throughout all of eternity, right, or infinity, from negative infinity, f just decreases. And then from our critical value to positive infinity, f just increases. So if there is going to be a point that's going to be lower than 1.5, I don't know what it could be. So here's another way that we could justify that not only is this a local min, which is essentially what the first derivative test guarantees, but in fact, it's an absolute min because over the whole interval. So if I said f decreases all the way from negative infinity to 1.5, and then f increases from 1.5 to infinity, therefore, right, we're talking about everything in the domain, f has an absolute min at x is 1.5. So here's another method, and on the AP exam, they do want you to be aware of what's going on at the endpoints, right? You're looking for an absolute min, not just what's happening in the area. So this is a perfectly good justification, as well as this. Okay, another way you could do this is, let's take our second derivative. Our second derivative is 2. When the second derivative is positive, the function is only concave up, ever. So if I say f of x is concave up over, and again, notice I'm listing those endpoints from negative infinity to positive infinity. Therefore, the one critical value that we have must be an absolute min. Okay, and that's the third method to justify